So guys, as I continue, I thought I'll mention that your course portal is up to date. So today's topic, which is visual language understanding, if you look at it, I put some notes here, little bit of notes. It may be a summary of what we have been talking. There are some things that I haven't talked about today. I'll talk about the next time, but I've just put some notes here for you to understand. If some of this math doesn't make sense, don't worry about it yet. Much of the visual language understanding, actually, I'll teach the next time. Today, we are just laying the foundation. But something I would like you to do. The first thing is, there is the CNN explainer. This is to see how the CNN is thinking and all these things that we talked about, you'll see it here. So look at this picture. This is in 3 channels, red, green, blue. Do you see this? So let's take it something, boat or ladybug. So let's read it backwards. You notice that it is saying the probability of ladybird. So if you see the scale at the bottom right, scale is from 0 to 1. This machine, this network, is very sure that this is a ladybug, isn't it? It's not saying it is something else. Okay, we'll come to this later on. Interactive. Okay, let me close this for the time being. It is ladybug. It's pretty sure. The question is, how did it become so sure that it's a ladybug? It is not saying it's a bell pepper, little bit. It's not saying it's a school bus, not a school bus at all. Do you see that? Right. And now, we will focus on only one channel, red channel. Let's look at the red channel. Look at what are these? The first layer contains a convolutional filter, convolutions. It contains a ReLU. Actually, there is no pooling happening in this layer. Pooling has been skipped, isn't it? But in the second layer, there is pooling. Do you see that they are doing pooling? So convolution, what is the activation function they are using? ReLU. Then third, no pooling. And fourth, again pooling. So people do that sometimes. They'll pool and not pool. So let's look at the ladybug. Ladybug is big red in the center, isn't it? Now, when you do the convolutions, here is how to interpret the value. The values are from -4 to +4, right? For each of them. So red is -4. This particular filter, right? Now see how these filters, they all try to understand. If you apply, first look at the blue filter. What is the blue filter doing? The blue channel. Blue channel is going through all of them, and look at what this filter is coming up with. Is there much blue? Like when you look at the signal, there is not much blue in the image, right? Is there? Right. So you don't expect that it will add up to much of signal here. Does that make sense, guys? Right. But on the other hand, if I were to look at the red channel, actually, let me do it. Yeah. Let's look at this. Do you see this tiny little thing moving around? Right. So suppose I put my mouse at a certain place here. I leave it there. So the numbers that you see in gray, as I move it, do you see those numbers keep changing? What are those numbers? Those are the actual pixel values, the red values in different locations. So for example, where was the ladybug red? dead center, right? She had a red coat, red wings. And so this ladybug, if you look at the numbers inside those boxes, they are all big positive numbers. Where is the filter? Where is the G that it is being convoluted with? It is these little boxes, colored boxes sitting underneath it. So if I put my mouse here, at this moment, this filter is coming out with a positive or negative value there. Negative value, right? Whatever this filter is, it is saying that I have, so this filter is looking for some feature that is not here. On the other hand, if I take this guy and I take this, now let's look at this filter. What is this filter doing? When I go to the red, you notice that red areas and these areas, they tend to have a positive value. Right? It's taking on slightly bluish tinge here. I don't know. It's very faint, but it's sort of visible, right? Where my mouse is, it's a little bit bluish. Those are positive values, right? Anywhere here is positive value. Right? It's picking that up. So this is how these filters go. But if you go back and look at the network, each filter is looking for whatever it is looking for, right? And it's not very obvious that it is necessarily looking for an edge, right? It's looking for something. They all decided that I'll look for this and you look for that, right? For example, it seems to me that this filter is looking for red and yellow, like bright colors. Let's look at this. And if I click on this, or yellow is made, how is yellow made? RGB. Red and green, is it? How is yellow made?
RGB.
Okay. Yeah. No blue, right? No blue. Okay. Let's take something that is blue itself. Something that's very pronounced with blue. Blue is not there in the image at all. Green is not there. So it has to be. So wherever there is red and yellow, anything that picks up red will also pick up yellow, isn't it? Pretty much. So it seems to be doing that. Look at the picture from the red channel, what it picked up, and what it picked up from the yellow channel probably is even more pronounced. Here we go. So this is how these networks work. But as you go down this, this becomes more obvious. If I take a cup of coffee, let's take a cup of coffee. You see how these filters are acting, right? Now, see what max pooling is doing. What does the max pooling do? It picks out the strong signal in the neighborhood. It sharpens it up a little bit, right? Then max pooling layer 2. So it becomes a little hard to understand the filters just by seeing their operation from this perspective. Like you cannot say that in the classical computer vision, it's an edge detector or it is a this or that detector. One of the best ways that I found to understand convolutions, first is play with this, guys. Play with all of this. Read how they have done. See what it does to the images. You can put your own image here and see what it does. Then, when you come to the course page, you see Chris Ola's must read on feature visualization. I found this article to be really very good. And one of the best explanations I have seen on what is the neural network itself, CNN, how is it looking at the world, right? So I won't go into it. I'll just give you a flavor. This is how the CNN actually looks at the world. You see these images, right? This is its, for example, understanding of flowers, right? And people have created beautiful art out of all of these internal representations that the CNNs are making from these images. So play around with it. I'll close the topic of CNN shortly. Now, I must mention that people have created really deep networks with CNN, Inception. So the big ones are ResNet, BGG, and Inception, right? These are really at one time before the transformers came by, there was a tremendous amount of excitement and tremendous amount of activity. Just before I close it, I'll give you an idea. By the way, your homework is this. You need to write a classifier that can tell, it's a very basic example, a pepper tree apart from a weeping willow. Right? Hand create your own CNN, compare the results to a simple feed-forward network, right? Do it using board and see how well the CNN works of yours.
Pepper tree from a willow.
Willow, yeah, weeping willow. So the reason I gave you this problem is they have some similarity. Their leaves, it's not that I'm asking you to compare banana leaves with a pine cone, right? A pine tree. So there is some degree of similarity. So it's a slightly hard problem, the network, how well you can solve it. The second problem, the second part of that is called transfer learning. It is in the world of CNNs that people first created the concept of transfer learning. What they would do is they would take a big CNN like Inception, like ResNet or VGG, and feed it through millions of data, train it on millions of data, images, and do some simple task of classification or something like that. Once those models were trained, they had a pretty good understanding of images or representation learning. But then they would release those models. Those models are foundational models, or what you would call pre-trained models. For many tasks, they do just fine. But if you need to get extra juice out of it, an extra bit of performance, what you do is you can fine tune, like for example, in this particular case, you can fine tune them further, right, with your data set to increase the accuracy on your problem. So I will ask you to take one of the well-known, pick any of the ResNet family or BGG family or whatever.
The third one is
Inception, which is big, by the way. So don't try it on your, it might be a bit hard on your local machine. Take one of these pre-trained models and do what is called transfer learning. Namely, you take a pre-trained model and you train it a little bit further. It's called fine-tuning on your specific data. When you fine-tune on your data, a few hundred data points are enough. Right? So for example, 200-300 pepper trees, 200-300 weeping willows are more than enough. Right? And we will release the code, or maybe at some point I'll walk you guys through the code. Do this exercise, and then I'll give you another exercise to do, which is a bit more interesting. You know that sound is captured as audiograms, right? Sound waves. And any function, any time series can be Fourier transformed. You can get the frequency components out of it. So usually sound waves, its transformation leads to something called spectrograph and spectrograms. And there is an image that you can make out of sound. These are called, and then if you align it with human hearing, these are called MEL spectrograms. MEL spectrograms. Let me write it. MEL spectrogram. Right? You need not do the MEL part or do it, whatever. The libraries are all there in the Python open source. I want you to write a classifier that distinguishes the chirping of a bird from the barking of a dog. So given a sound, it should be able to tell, was that a bird chirping or was that a dog barking? with CNN, see how far you go. Try it with a model of your own. So let me write down the homeworks. Some of it, I'm inclined to make it classwork, but I notice it's 3 o'clock. Classwork. But this is the work for the week, guys. A. What is the first homework I gave? Yeah, exactly. Weeping willow, right? And one thing you might want to do, guys, do crowdsource it. All of you put together your images, pull from the entire batch, right? Create a common place where you post all the images. Maybe I'll open up a Google Drive, put pepper tree images there, put weeping willow images there in one place. Be careful, don't use copyrighted images. And standardize the image to some size, let's say 224 pixels, or you can make it 512 by 512. Pick some standardized size, doesn't matter, right? B, do it using feedforward network. Those of you who come from the Thursday session, I hope we didn't give out the solution. We just showed it to you. Or did we give out? We already gave out. Okay. Do it with of your own. Third, use transfer learning and fine-tune an existing pre-trained model. Right? From Hugging Face. Get a pre-trained model, fine-tune it. Are we together? Right? This is your first homework. Second homework is repeat this exercise with barking dogs, with sounds of versus barking dog versus chirping. Chirping bird. Is it a bird chirping or is it a dog barking? Do this, guys. Trust me, you will learn a lot. Right? And in anticipation for what I was going to teach you today, you can also try it with transformers. That's your next stage. But if you're not able to do it with transformers, at least this much, try to finish it before we meet again. Before we meet again, try to finish it. And do it as a team. We are all teams. This is what we need to do. And crowdsource, I must say, crowdsource your data gathering. So if anybody finds lots of data sets of animal sounds, share it with everyone.
Do you have any location?
I will open up such a location. I'll open up a Google Drive. You guys can all dump it there. Right. Now, guys, with that in place, we'll a little bit of a very short bit of history. See, CNNs were not very much in vogue. Neural networks were not in vogue in computer vision. Like I told you, I have textbooks on computer vision spanning more than 2 decades now. If you look at the textbooks before 2010, most of them they don't have as much coverage of CNNs or transformers or any form of neural networks as books have today. Today, neural networks are moralistic in large parts of computer vision. So the way, there's a little bit of history, the way these things came about is interesting. The big movement came with AlexNet. Jeffrey Hinton and team, they observed that Fei-Fei Li here at Stanford was creating the ImageNet dataset. So they wanted to show that neural networks really work, CNNs really work. So they did an interesting bit of game. They knew that any paper that used neural networks had a tough time getting accepted in computer vision journals. Can you believe that? There was such a time, right? So they actually, they went to these big guys and said, okay, would you agree that ImageNet is a good benchmark to compare computer vision algorithms, right? So those people said, all right, we'll grant that ImageNet is a big effort, lots of images, right, of everything. And so it's a good benchmark for image classification and related tasks. So once it was accepted, then they came out with their paper showing that actually neural networks work great. And in fact, it beats the state of the art. But two things happen. First is CNNs are massively parallelizable. Do you realize that all of the filters can be applied in parallel through the data? They're just matrix multiplications, right? In fact, and likewise, all the, even a particular filter can be applied all over the patch, all over the image, more or less in a parallelizable or decomposable way, right? It can be sharded and done quickly. So it was one of the first tasks in AI that was massively parallelizable, which meant that when you look at those times, we are talking 2012, what could do very good vector computes? They were in the gaming industry and video content creation industry, right? So you would use that to play games, to play all of these games, right? They did a lot of matrix multiplications. And so NVIDIA, which was a company making graphics card for gaming and video, all of a sudden found a new market, the AI community. And they latched onto it. They realized, oh, this market is, we can really sell our products to this market. Then 2014 is, I believe, when when ResNet came on, so with residual connections from Microsoft. It's another Alex. So the big movement came around 2012, 2014, at this period, when many things came out, AlexNet, ResNet, GANs were discovered, generative adversarial networks, etc., were discovered all in a short 2-year period, right, 2 3-year period. And it was considered in computer vision the moment. The reaction was mixed. There were people who were absolutely thrilled from a practical perspective, right? You notice that on, for example, the MNIST dataset that I mentioned, you beat humans completely. Beating humans is a big thing. Like today, for example, when we say that these tools are able to do a better diagnosis than human beings can, it has profound consequences, isn't it? Now, these networks have become so good that MNIST is now considered a useless benchmark. Because it is trivial with these algorithms now to achieve 99.9 plus percentage accuracy. Right? It's become, so you have other benchmarks to judge.
What is this percentage of
today?
Yeah.
It's 99.9 plus. Right? You can look it up, MNIST benchmark. Maybe we can look it up together if that interests you. No? Let's go.
Benchmarks.
Yeah, but MNIST is now considered not really a very serious benchmark. But good point. I haven't checked it myself. MNest. Best accuracy or MNest benchmark. Yeah. Oh, some of these are saying 99. Okay, 99.87 accuracy is some merging CNN plus homogeneous vector capsule 0.84. So this is image classification on MNest. You notice this, right? So you notice that most of these algorithms, they have close to 100%. Right. So as I said, I exaggerated. I think I said 99.9. It's 99.87. But when you compare it to human, it all becomes sort of meaningless almost. Human beings, maybe they should put human beings somewhere in the list. It's not even in the list, right? So this is it, guys. Can you imagine something that was considered for decades the challenge, the hard problem, has now gotten trivialized? And see how many of these are all convolutional networks. VGG, by the way, is something that you guys should try out. So guys, try to solve your problem with, this is it. Let's see. Like, there are lots of articles. If you go way back, right? People at that time used to even think about how to do that. Like 2020, you see, going beyond 99% used to be an article. Today, you just assume that accuracy has gone so far beyond. So that is that. Now, the three networks that I want you to try out are try ResNet, a small ResNet, ResNet 50. Try AlexNet, try this. Try ResNet, VGG, pick your VGG, whichever, VGG 16 or whatever. Pick that and pick Inception. Now, with Hugging Face API, all of this is as simple as just changing the name of the model that you download, isn't it? So try these things out, guys, and try to fine-tune them. And with that, these things like when ResNet came out, VGG came out, look at their architectures. They're fairly deep architectures, like many, many layers. Inception V2 in particular shocked everyone, like how deep it went. Right? Many, many layers deep. So that is the state of the art with CNNs at this. Right? After that, people have hybridized CNNs, hybridized it with other things to get good results. And I won't go into it. I'll end the topic of CNNs now that you have your homework and everything. Any questions, guys? Did you get the main idea of a CNN?
Yes.
Right, we got it, right? Yeah. Yeah, go ahead.
You can go to that playground.
Yeah.
CNN. Maybe you can explore it. You can explore it.
Yeah. Right.
So we'd like to can talk through the architecture. So they're primarily taking, so we looked at mostly black and white.
It's just four, yeah, it's just 4 layers.
Now the input is each of the colors of matrix are separate, right?
Yeah.
R, G, and B.
Yes.
Yeah. The data comes in that form, right? And
yeah.
Can we adjust the number of neurons in each layer?
No, they don't give you that. They don't give you. It's a very fixed layer.
Fixed.
Yeah. Yeah, it just says it's an explainer. This is what is happening inside.
Oh, that's mainly in each of them, it's a number of filters. That each layer is filtered, right? The convolution.
That is right. Each of these boxes that you see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, guys, in reality, you don't do like this. What happens is that in real neural network, many things are different. As I said, as you go to subsequent layers, you keep increasing the number of filters. And because your feature map becomes smaller and smaller. So why don't I do that? That may be instructive. Let us look at the original LeNet. Why is it called LeNet?
It's used Jan Lekon.
Jan LeCun. Yeah.
So I had a couple of questions that we can cover. Is how do they make the decision of number of neurons in each layer, the convolution?
That's a hyperparameter of the model. In fact,
And also decision to pool or not to pool.
yeah, in my case, I generally pool always. Like rarely do I skip pooling. So look at this. This is more typical of what you do. Do you notice that it is only two-layered neural network? By today, this is 1998, guys, or something like that. Very old.
Oh.
Right. One. So how many filters are there in the first layer? 6. Image sizes, how many pixel by how many pixel? 28 by 28, right? Because there wasn't enough compute resources. This was already brutal computation, right? And I think they used average pooling. This architecture uses average pooling. The one thing that you don't see is, of course, the activation, which is implicit, right? Then what happens? Do you notice that after the pooling, the size of the picture decreases? It has become much smaller, right? After the, right? And if you look at it, it's implied, but this also is a little smaller than this. And then you're convoluting now. Initial was with 6. Now you're convoluting it with 16, isn't it? If you convolute it with 16, then you do the pooling, you end up with a smaller feature map. So first you go from 28 by 28 to 10 by 10. Then after pooling, it becomes even smaller, 5 by 5, right? And this 5 by 5, what you do is you take all these feature maps, linearize it, and make one giant long vector. Do you see that? This is one giant tall vector. So that is going into a feed-forward network, 1 layer, 2 layer, and then the last layer would be your softmax, because how many digits are there? 10. So there are 10 digits. So you go from 180 to 84 to 10. 10 is, of course, obvious. These are your decisions. So, for example, if you're doing a LeNet, redoing LeNet, you can play around with it, guys. It's a fun exercise, actually, to create your own LeNet from scratch. These days, with PyTorch and all of this, the entire thing you can write in about literally 1 paragraph of code.
Something is like one image. Like
one image, yeah, one image.
Not in that image is no one image. That the first.
Yeah. It's black and white. It's not RGB. Yeah. And he's going through all this process. So this is the LeNet architecture. Relatively speaking, and here it is.
One
Yeah,
question,
yeah.
Again, you use the average for pooling. Those are the
in those days. These days, actually, people they prefer max pooling or min pooling based on whether it's a dark or light image. So there's a lot of contention which one to use. Many people believe it doesn't matter. Some people are very, very, fixated on it and so forth. So as everything, everything is up for debate. And this picture that you will see is the same thing. Oh, look at that. Already you can see that by the time subsequent versions of LeNet came, they're using max pooling. You see max P. They chose to go with max pooling. The rest of the details remain exactly the same. Oh, no, it became not, 14 by 14, 10 by 10. Yeah, the rest of it is more or less the same, right? So LeNet was the classic. Let's compare it to some, let's take the other end of the spectrum. What does a VGG net look like? Not VGG, Inception. V2. Oh, V4. V4 architecture. And it is so big that you can't even represent it. Each of these are pretty big. Let's see, somewhere in the code, let's go to the original. Okay, maybe in the paper, they would have said that. So things change because now you see a lot of residual connections. But you look at the architecture now, right? It's so big that you have to explain it in pieces. right? So there's a lot going on here. And what kind of pooling are they using? Somewhere, I think they are still using max pooling here. But you can read this, guys. All of these papers are available. Once you become familiar, it's not that hard to go and do that. VGG architecture, image. Okay, somebody has written an article on it. You notice that it is pretty deep, layer 7, right, and softmax. But by Inception standards, it's still small. Yeah.
So, as a feedforward network that we need to compare with, what are the number of layers that we recommend or do we get that from model from the Hugging paper?
No. Come on. By the way, let me just put it this way. In this homework, where is the homework one? At the end. Yeah. The one, write your feed forward by hand. 2, write your convolution by hand. And only in 3, use transfer learning. Yeah. And fine-tune an existing model from Hugging Face. Right? So see, the ideas remain the same. They just become bigger and more sophisticated rewiring. You have residuals. Residual connection is something, and its value, why is it important, is something you learn in the foundational course, Intro to AI, not here, because we won't have time for that. Now, I'll wrap up CNNs, right? And I'll give you guys no more than a 5 minutes break. Then we'll learn about an entirely different approach to do this using transformers. So far, we have been using transformers for words, for text. Now we'll use transformers for images. So, and we will read the original paper. So let's take a break and we'll meet again.